And the final thing we're going to talk about for spring break is about even and odd functions. All right, so you may or may not recall these definitions, if I can spell definitions correctly. All right, but an even function means it's symmetrical about the y-axis. So, whenever you think about even functions, think about x to an even power. So if I have my axis, x squared, looks like this. All right, and you can see it's a mirror image over the y-axis in the middle. So if I knew just the right-hand side of this graph, I'll just flip it over and I'd get the left-hand side for free and vice versa. All right, so that's an even function if the left and right hand of the graphs are mirror images. An odd function, and again, for an odd function, you want to think of x to any odd power, x cubed being the kind of ideal one. If you were to graph this, it looks like something like that. And these are noted as symmetrical about the origin, all right, the point in the middle. Because if I have half my graph here, if I kind of spin it around the origin, all right, then it'll become the second half of the graph down there. The exact definition is that if I plug in a negative value, that's negative of the positive. So if I plug in the positive version of this, I get this number up here. Plug in the negative, I go down instead of up and down there. All right, so it's kind of flip rotational thing with odd functions. All right, but those are the basic ideas, and with graphs, you can kind of tell how are they symmetric or whatever. There's a nice property when we relate these to integrals. All right, for an even function, all right, so again, we'll just think about x squared as our example. If I want to find the integral from negative a to a, so the negative of the same value, I'm finding this area under my curve. So I'm trying to find that. But I can shorthand that. Because it's the same picture on the left and right, this area here is the exact same area over here. So instead of doing this big problem, I can just find the area from the middle, 0 to a. And if I know this area, I just double it to get the whole thing. So I just do 2, and I do it just from 0 to a instead. So if you recognize your function's even, you can simplify it. And doing things from 0 most of the time is going to be a little bit simpler because plugging in 0 is a nice value. So if you recognize your function is even, you can simplify your problem a little bit. With odd functions, it's even nicer because if I have my odd function, again, we'll use x cubed as my example, and I want to find the integral from negative a to a. All right, I'm trying to find the area here and there. All right, but because this function is symmetric, this negative area below the x-axis is a negative answer. This is a positive answer. But because it's symmetric, they're the same number, just opposite of each other, so they're going to cancel out and just give me 0. So if you ever integrate an odd function from a negative of a number to that positive, you're just going to get complete opposites for the areas, so they always cancel out and you always get 0. All right, so sometimes on the AP exam, there'll be this really hard-looking integral for something with like a sign in it. Oops. Some odd power effect, something like this. This would be a really hard problem to do any other way, but if you recognize sine ends up being odd, x to the 5th is odd, so when you put it all together, this ends up getting you 0. And actually, I think I messed up. I might need to put like an extra x up here, all right, to make it actually make sense. But the basic idea is if you recognize that your function's odd, you don't need to do any integration using any of the integration techniques we'll talk about after spring break, any of this stuff. Just recognize it's an odd power, the bottom bound and the top bound are just opposites, you get 0. There's always like one of those problems on the AP exam. So this is one kind of extra fact about integrals with specific types of functions that'll help us.